Alright, so in this video we'll begin section 12.4, which is space curves and their lengths. Loosely stated, a curve C is smooth if it has no quote-unquote sharp corners or cusps. A piecewise smooth curve is a curve that can be described by breaking it into finitely many smooth curves. So you'll see the terms smooth and piecewise smooth a lot throughout this section. There's an official definition in the textbook as to what smooth means, and I'll do one example where I briefly use that so you all can read that definition. Now, there's also an example in the textbook that uses the actual definition of smooth as well, so you'll see that in your reading also. But I just wanted to give you a general idea of what it meant, more so than the formal definition. So let's say we have our set of coordinate axes. And I'll sketch a smooth curve on here, and I'll sketch a piecewise smooth curve on another set of coordinate axes. So say I have some curve, and you can sketch your curve however you want to, as long as you don't have any cusp in your curve. So that's my curve C, for instance. And we're going to still continue to include the direction of travel on our curves. So this curve is smooth. And say I have some other curve. So this curve is piecewise smooth, just because I have this one smooth curve and then I have another smooth curve, and they just join at that point right there. But each one of the curves is smooth, which makes the entire, each part of the curve is smooth, which makes the entire curve piecewise smooth. All right. So, and the really is our rationale in using smooth and piecewise smooth is that in this section, we're going to start doing lengths of curves, and we need, in order to be able to evaluate the necessary integral, we'll need our curve to be a smooth curve. So that's why I didn't give the formal definition, because for the curves that you're going to actually find the length of, they already will be smooth. So it's not really something you're going to have to be too concerned about, but you will see that wording a lot in the section. So now let's talk about how to find the length of a curve. Let C be a smooth curve. Suppose the vector function R of t with components x of t, comma y of t, comma z of t, where t varies between a and b, traces out the curve C exactly once as t varies from a to b. Then the length of the curve C is L equals, and we just use L to denote length, the integral from a to b, the square root of x prime of t squared plus y prime of t squared plus z prime of t squared with respect to t. Or that can also just be written as the integral from a to b of the length of the vector r prime of t with respect to t. So then we'll talk about the arc length function, which is very similar to the length formula that we just did. So if a is a fixed value in the domain of the vector function r of t, the arc length function is, and we denote this by S of t, equals the integral from a to t of the magnitude of r prime of t. Or sorry, I need to use something else, not t. I can't use t because I used it right there. Let's say r prime of u. Sorry about that. So I can't use t because I used it as one of my bounds. So the magnitude of r prime of u with respect to u, where t is some value greater than or equal to a. So this just gives you instead of taking the length of the entire curve, you can take the length of the curve from any point A in the domain of r of t to some other point t. So in this, of course, this length of that portion of the length of that portion of the curve, is going to vary with regards to whatever t you choose to plug in. So that's why this is a function. So the length of the portion of the curve between r of a and r of t is S of t. So that's all we're getting there. Note that the derivative of s with respect to t equals s prime of t, which just would be, so if we were to take the derivative of this antiderivative or this integral with respect to t, we would just get the magnitude of r prime of t. All right, so I'm going to stop this video here because you have a couple of things so far just linked, and then in the next video I'll do a couple more notes on parameterizations, and then we'll work on examples after that.